Hi, it's Brady, and today I have a fun problem to show. So a ball is thrown with an initial speed of an initial velocity up an inclined plane. The plane is inclined at an angle of phi above the horizontal, and the ball's initial velocity is at an angle of theta above the plane. Choose axes with measure of the slope and y normal of the slope. So I didn't draw it in my diagram, which is pretty bad, but we're gonna have our x-axis along the slope as opposed to up and down, and then Ry is just gonna be normal, like a normal like friction problem, where you would have the normal force. Ry would be that axis. So write down Newton's second law using these axes and find the ball's position as a function of time. Show that the ball lands a distance of r, 2 times the initial velocity squared, sine theta, cosine theta plus phi, divided by g cosine squared of phi, from its launch point. So first we're gonna find our Newton's second law equations, which is it's actually pretty simple. We just um, have to account for the components of each angle here. So since our axis is along the horizontal and our y is here, the the acceleration of our projectile is still gonna be relative to the slope. So the component would just be the phi angle component, and then our velocity is just the angle at which the projectile is thrown. So in this case, it's a ball. It's kind of complex with this phi right here, but like I think it seems a little simple once you start thinking of it as in terms of the acceleration is related to the phi angle and the velocity is just the theta. I think that breaks it down a little easier. So next we're gonna go down to get to this range part. So first, we're gonna start by setting t equal to 0, and then I just took t out from the y equation, from the last part of the problem. I just took t out. So then we can just set this inside equal to 0, and then we just separate, put them on both sides of the equation, and then we move it over, so we just can isolate this t here. So now we have a general equation for t. So this is so we can use this to put it in our x equation. So since like again it's along the x is along the slope here, we just need to put the general equation for t into this x equation. So we're gonna put that equation we found in this t right here and this t right there. So let's go back. So here we have our x equation. So we're just gonna put this equation for t into this t and this t. So first I factored out the t, like I did in the y, and then it's just plugging that general equation in, and then since there's a v initial in our t, that puts a v term, velocity term in our second term, so we can factor that out too. And there's a g on the bottom and a g on the top, so those cancel. So we're left with the initial velocity times the cosine minus the sine of phi times the sine of theta divided by the cosine of phi times this other t term right here. This is just the other t that we factored out, like this other one. And so we're gonna bring this. We're just gonna bring this velocity and this gravity to the front, and then we have all our trig functions right here. And then so this is actually just a trig identity, so that we can just use our trig identity here to simplify the problem a lot. So our trig identity is the cosine of alpha plus beta is equal to cosine alpha times cosine beta minus sine of alpha times sine of beta. So if we have this, we can just represent it as that. So we have that. We have cosine theta, cosine phi minus sine of theta minus sine of phi. So we can just write that as the cosine of theta plus phi. So putting that into our equation, just changing the trig identity, we'll have our range equation, which would be 2 times the initial velocity squared, so we bring out 2 v terms right here, the cosine of theta plus phi, that's just our trig identity, and then our g term, because we still have since this g canceled out, but this one's kept it in our equation, so we still have it here, and then we have a cosine squared of phi, because we had 2 t's, and there's 2 cosines of phi's at the bottom, so that we just have the cosine squared of phi. And we'll just check that from our original problem. See that yep, we got it. We were able to derive the range along the x here, along the slope. So if you're shooting a ball up the slope, we have an equation for the range here, so we can know how far up the slope that ball would go based on if we knew our initial velocity, the angle at which the projectile is thrown, and then our angle phi here, which would be the angle of the incline. So lastly, I have a problem to kind of show this range equation that we derived. So a Roman velocate is tasked with launching his javelin up a 12.5 degree incline to hit a hoplite that is 65 meters up the incline. If he throws his javelin at a 45 degree angle, how fast will he need to initially throw the javelin in order to hit his target? So this is just simple, since we have that equation that we derived, and he just wants to throw his javelin up the slope. So we just have a basic equation for the range of a projectile on a slope. So all we have to do is just plug in all our information here. So we know that R is 65 meters. He's 65 meters away. We know that our theta here is 45 because he throws the javelin at a 45-degree angle. And then we know our phi is 12.5 degrees because he's on a 12.5-degree incline here. So we just gotta plug that back into our formula here. 65 to velocity squared times 45. Just add these angles, put that in. It's pretty straightforward. After some algebra, v squared is 799, and then you just square root. The initial velocity would be 28 meters per second. So he would need to throw if he threw his javelin at a 45-degree angle up the horizontal, he would need to throw it at least at 28 meters per second. That's how fast he would need to in order to hit the little hoplite up there. All right.